gonna score like homework for the computer. I really like that this week. Because both proofs and props were totally doable, but sometimes they're not. So. Although I'm kind of peeved with he's starting to weekly homeworks. And he often won't get them back to us.
I figured that out this morning, and I was like, I looked up to you.
He often won't get them back to us until the next Wednesday, which is like, I guess fine. Like, proofs can be a lot to grade. But like, it's kind of annoying to like have to hand in the next homework without seeing your feedback on the previous. And then, but whatever. But then this Wednesday, we have our homework tomorrow. So now we have like 2 homeworks where we have no idea how we did. Oh, I mean, this week's homework is pretty easy, so like, but like, I feel like, well no, next week buddy's, he actually did get an extension. He's making the homework due Friday instead of Wednesday just because of spring break. Like, what's the point?
Yeah.
If our homework is due Wednesday and we have to go to class Friday, we checked it.
I did. It was year one.
Right.
Yeah.
So today we're going to talk about normal distribution. As a probability distribution, calculating areas, and then use some of our techniques like moment generating functions to look at what happens when you add normals together, what happens when you scale normals, and things like that. Right? And so this will be the last part that we do in this chapter. There's a couple sections that we're going to skip for now. One's called reliability. Another way of looking at some probability distributions, and there's one which a section on missed distribution functions, where you might have a mixture model where you have 2 different groups or 2 different distributions, and it's all meshed together, or some measurements are more discrete, like you have a bunch of zeros, and then you have some positive values. So those are interesting. But we're not going to talk about those in detail right now. But I encourage you to look through there to see what's in there. Eventually, we'll talk about projects for the class, where you get to investigate something of interest to you or apply the methods related to probability distribution, either to data or in a theory setting or in simulation. And if one of those particular sections looks really quite interesting to you, a project could involve looking at some of the problems that are associated with those, some of that, and maybe doing a little enhancement to that more. So it could be kind of a motivational thing. If it really clicked and said, wow, I wish we were doing that, you could do it as part of a project. Right? So after this, we'll look on next Tuesday, we're going to look at something beginning in chapter 6, multivariate distributions and combining distributions and variables. So for normal density, the probability density function for a normal distribution is the curve that is the familiar Bell-shaped curve. The equation for this thing, if it has a mean mu, entering at some value, and a standard deviation of sigma, the density at x, the values of x go somewhere, anywhere on the real line, negative infinity to positive infinity, has 1 over 2 pi sigma squared, square root of that whole thing, e to the negative x minus mu squared over 2 sigma squared. Right, and so that thing ends up producing this curve. The height of this curve here is the density, right? And this curve, the area under the curve, like all densities, total area under here is 1. And the probability that your random value is less than something or greater than something or in some interval, right, is determined by the areas. Right? So that's what that looks like. If the mean is, the thing that we'll see is, for normals, is everything about probability is really determined by the mean and standard deviation, the relative areas. So whatever they are, you get up here to about the mean plus a couple standard deviations, down to a mean minus a couple standard deviations, and you get about 95% of the area in here. So approximately how much would you expect to be out in each of those two tails? Right? Less than the mean minus 2 standard deviations. How much would you expect to be over here? It all adds up to 1, right? And there's 95%, 5% left over. Right? The normal symmetric, I didn't mention that, but it's symmetric about the center here. So the area below this value or above that value is exactly the same. So if there's 5% left over, there has to be 2.5% out here. And similarly, in this tail up here, there's about 2.5% out there. And whatever the mean and variance are, these same ratios of areas persist. So we look at a special one. Right? If the mean is 0 and the standard deviation is 1, it's usually called a standard normal distribution, usually denoted by Z. So if Z is standard normal, then that density for Z simplifies. There's 1 over square root of 2 pi, e to the negative Z squared over 2. That thing is centered at 0. And these limits were for the value of Z. And this is this thing for the standard normal often gets a special name, a little symbol for that density. It's just such an ubiquitous distribution that people use that as a special symbol for the standard normal. So this curve is like that. And about plus or minus 2 under the standard one is about 95%, with 2.5% under each of these curves. The cumulative distribution for this one, just like any other cumulative distribution, the probability is from starting from negative infinity up to some point we're interested in. And that was, so the CDF, cumulative distribution function, so the probability that a standard normal is less than or equal to X. So let's do the Z one first. The probability that a standard normal is less than or equal to a value if Z is distributed like a standard normal with a, it's usually written like this, with mean and standard deviation or variance there, is the integral from negative infinity up to some Z value of that 1 over 2 pi square root e to the negative Z squared over 2. dz, I guess you would put a little Z star up here, right? Just to make these two symbols look a little bit different, right? So it's that. This one for a standard normal gets also a special symbol associated with the capital V of Z. And like any CDF, it slopes up and then kind of asymptotes out here at 1. This one is the halfway point here of 1/2. halfway up, it's at its mean, which is 0 in this case, and this is the graph of that thing. Right? Now the integral of this is not something that we can do directly in one dimension, right? So, but these things are tabulated. Yes?
What is the exponent that the e is raised to? Is it z squared over z?
Z squared over 2.
Oh, okay.
Yeah.
Thank you.
That's right. So these things aren't generally available, right? I mean, we can't do this in closed one, we can't write it out and do it. But these things are tabulated, and that's the purpose of the tables, right? That these things have been tabulated. And if we translate any question we have from the normal on its original scale of measurement back to the standard, so-called z-scoring or standardizing it, we can look up these cumulative probabilities by the table, or something like the cumulative probability. So let's illustrate this in an example, right? So let's say among mothers that birth weight among term births, right? So term births would be 37 weeks, at least greater than or equal to 37 weeks in terms of gestational age. Let's say that the average weight of the babies is about 7.5 pounds, and the standard deviation of weights is about 1.2 pounds. And among these, let's assume right now that it's approximately normal. Maybe term birth, so full gestational age, no really severe complications, So we're kind of limiting it to a set of births and pregnancies, and also singletons, say. Right, so there's only one baby, not twins or triplets. If there were complications or it was early, there'd be this long tail of births that came in at really low birth weights, and the distribution wouldn't be quite normal. But among this, kind of restricting it, it might be reasonably normal distribution. Now, of course, it doesn't go off to positive infinity and down negative infinity. But if most of the probability is really in the core center of that distribution, it works pretty well for calculating probabilities, except at the very, very extreme, right, that it might not fit so well, right? So, but if we have this, we can ask something, what's the probability that the weight, let's say the W is the weight, right, is less than, say, 5 pounds? What's the chance that a baby's born with this restricted group, but still has a weight less than 5 pounds? So we're going to standardize these things. We're going to subtract the mean and divide by the standard deviation to get back to the standard scale. Mean 0, standard deviation 1. And so in this case, minus 7.5 divided by 1.2 is a z-score of negative 2.08. So our question about normal areas on the original scale translate into a 1 on the standard scale. Right, so it's less than 2.08. And so we're going to look up something related to negative 2.08 on that standard z-scale table. Right, so let's draw pictures. Right, so on the original weight scale, we had an average of 7.5. And we're asking, what's the chance that this baby's born with less than 5 pounds? So we really want that area. So we can translate it into a standard one. Subtracting the mean centers us at 0. And dividing by the standard deviations translates this into standard deviation units. How many standard deviations is this value below that one? And it turned out to be negative 2.08. So we want the area below 2.08. Our book has given us a particular representation of areas. Right? Did we have a copy of this one? And so along the vertical axis, are z values, 0.0, 0.1, 0.2. Right? We get down here to 2, but we want negative 2.08. Right? The second decimal place in z is given up here. So 0.00, 0.01, 0.02, or, starting at 1 here, 1.0, 1.1, 1.2, 1.3. And the area it's going to give is not completely accumulative, right? It's not going to give the area all the way less, but just the area between 0 and that point. Right? So we have to use a little logic to figure out what's the chance that we're, say, below a point down this way. Right? If this is the negative 2.08. And the total area is 1, and it's symmetric. 50% is here to the left, 50% is to the right. Whatever area is below this is the same as the area above that. And so going back to our picture, we need the area below 2.08. But we don't have anything like that. The type of thing that we get, right, is an area that looks like this. So we're going to look up, right, the reflective side, we're going to look up 2.08 under the standard normal. And so let's look that up. What is the area probability here between 7.5 and 2.0 standard deviation? 2.08. What number did you see there? 0.4812. So if you start at the 2.0 row and go over to the second to last column, the 0.08, right, 0.4812. So that's the area between 0 and 2.8, right? So this area in here is this value. So how do we translate that? By subtraction, by reflexivity, right, into below 2.08. What do you think the area is going to be up here in that little tail?
Minus 0.4812.
Half is on this side, so 0.5 minus this, 0.4182, 0.0188. So this area is 0.0188 under here, right? So what's that area?
The
Same, right? By reflexivity, but it's symmetric. Right? We also get the area over here is 0.0188. So the answer to this question is 0.0188. 1.9%, almost 2% of the babies born under completely standard circumstances have weights less than 5. So it's unusual. Maybe there would be factors that would predict that. If the mother and father are both kind of small, or the previous births to a woman have been small, or something about nutrition and general health that would still put them in this category, but would tend to be associated. So it might be a little bit predictable. But other things being equal, it's kind of a rare event. Looking at this 0.4812, right, so under the standard normal, right, here was 0 and 2.08, 0.4812. Right. You can assign probabilities to other numbers too, right? So the probability that 0 is less than z is less than 2.08 is 0.4812 from this chart. So I'm teaching 3 classes this semester. We use a normal distribution of all. All 3 of them have different tables, right? Different ways of representing this, right? One gives the area below, right? So what's the probability that z is less than 2.08?
you do 1 minus what we got in the question before?
Yeah. So we could do 1 minus that. Right? So we figured that the probability that 2.08 is less or equal to c is less than infinity. Right? Well, I just cross that out, but just that it goes all the way up. Was 0.5 minus this, right? Or 0.0188 up here. So less than that, you could do 1 minus that number. You could do 1 minus 0.0188, so 0.9812. Right, is one way to get that one. Is there a second way to think about getting that one? That's perfectly fine. That would be great. That would be an answer, right? So less than 2.8 is that whole area. Right? What did we say the area on this side is? 0.5, right? So you could take 0.5 plus this and get it. So in all these problems, when it's asked you to do a probability, it's thinking about, you get to look up one thing on this table. I can reproduce this table and give it to you on an exam, right? If you want to calculate normal probability. The other way is less than 2.08 is 0.5 plus the 4812, which is the same thing. What's the chance that we're less than 2.8 or greater than 2.08 or less than negative 2.08? So in our first problem, right, we did the probability that the weight was less than 5 pounds. And we determined that was 0.0188. The average was 7.5, 0.5. We put 10 up here. Right. This area is 0.0188. What's the probability that the weight is more than 2.5 pounds from average? So it translates into less than 5, more than 10. So the chance that the weight is less than 5, or translates to plus, that the weight is greater than 10. Z-score, if you get two numbers like that, right, you can Z-score both. This is the probability that a standard value is less than negative 2.08, right, plus a chance that a standard value is greater than 2.08, because they're equal, it's the same number, because same number of standard deviation units plus or minus, because they're equal distance. And so if this one was 0.0188, this one's the same. So that's 36376. So 3.25% of the babies are born at those extremes, right? If this normal model works well for births of this type. But any questions about this? Right? So it's a logic of figuring out areas of it. What's the?
There's a question.
Oh, sorry. Yes.
How'd you find the value of z again?
The z is the z-scoring. Right? So say you would take the value, the weight of 10 pounds. Our z-scores, we're going to take that value and subtract the mean and divide by the standard deviation. And originally when the problem was stated, the average was 7.5. And the standard deviation was 1.2. Is that right? Was that it? Sigma of 1.2, yeah. So at the upper end, it's 2.5 over 1.2, which about 2.08.
So it's, okay.
So that was the upper one. The negative one is that many standard deviations below. If you put in 5, it end up being a negative of that one for the same distance. From this table, we can also look up percentiles. Right? If you have the cumulative distribution function, right, going from 0 to 1, it's centered here for say a z value, a standard normal. The cumulative distribution function, which had this special symbol. If we want to look up a percentile, some percentile here. So let's look up something like the 70th percentile. If we find the probability that's 0.7, and then I need to draw it a little higher to make it make sense. Draw it up here a little higher, because it's going to come down here, and it has to be above 0. At 0 is that here in 1/2. But if we are interested in the 70th percentile, then we can find that percentile and map it. Things are given to 4 decimal places in this table. So, and the things that are in the table are the percentile. Well, it's a probability. It's not quite a percentile because of the way the table's set up. But we can do this transition. So, what's the 70th percentile of a standard normal? What probability are we actually going to look up? Well, so here's 0. Right? Is the 70th percentile going to be above 0 or below 0? It's pretty clear this is going to be above, right? Because the halfway point is there at 0. It's symmetric. So we want to look up some point here that, if this is the 70th percentile. Below that point is 70% of the area. We can't look up 70%. We don't go that high, right? So what percent do we have to look up?
20%.
It's 20% above the mean. Right? So we're actually going to look up, 20% that's above. We already have, 50% below. So we look up that and figure out what z value it is, right? The value on the left, on the right. What z value seems to correspond pretty well to 20%?
0.2.
It's in the
0.502.
yeah, it's in the 0.02 column, right? And about 0.52, 0.53, something like that. So if you look up these things, where if the z value is 0.52, the probability area in that shaded area is about 0.18, 1985. And if z is 0.53, the probability in the shaded area is about 2019. Does everybody see those two numbers? Every once in a while, I get somebody after a while who asks, well, how exactly do you find that, right? It's fine to say you don't see it. It's good to ask early because we'll use this a few times. So, but just do see that you can find those numbers. So, if you have the computer, you can do it exactly. Let's use a value of z of 0.525, and that's approximately, and so the probability of this is about 0.2. Right? You can look up exact values. And in maybe a scientific serious application, you would do it to get a couple more decimal places, but it's probably going to be accurate enough. So the 70th percentile, right, is a z of about 0.525. But that's the standard one, right? We want to translate it into births. So the way we z-scored things is z was our weight value minus the average divided by the standard deviation. Right, if we undo that and solve for the weight, right, in this linear equation, we multiply by sigma, right, and then add the mean, and then it'll isolate the weight on one side. And so it works because everything's, all the relative areas are all determined by how many standard deviation units you are from the center. That you get the same percentile. You get the 70% of W by putting in the mean here and our z value, 0.525, times the standard deviation, which was 1.2, this here is in pounds. And so the 70th percentile ends up being I don't have that value on here, but we'll get, let's compute it. The next thing we're going to think about is, I'll get R going in just a moment. So the second question, we get the 70th percentile, we're going to ask where's the 30th percentile. But this value, we don't need this stuff. So 7.5 times the plus this z value, 0.525, times the standard deviation. So about 8.13 pounds. So 8.13 pounds, 70% of weights, of births in this category. So what's the 30th percentile? We need to find the z-score, right? And then we're going to use the same equation, but now with the new z value. So for z standard normal, 0 and 0.525, had about 20% of the area in here. And we translated that into the weight one, which is normal, with 7.5 and 1.2. I just want to note, different books will put either standard deviation or variance there. And so they'll tell you, they'll write normal, 7.5, 1.2. You have to know from the context if they mean standard deviation or they mean variance, because one's the square root, a square root square relationship there. I like putting standard deviation because it's in pounds. It's just directly translatable in there. But different textbooks, different articles will do different things, so you just have to know. But we translated this into 8.13 pounds. And that's the 70th percentile. And there was 70th because 0.5 plus 0.2 is 0.7, and there was 0.50 up to 0. So where's the 30th percentile? Yeah, so on the other side, right? How much? Well, on the z-scale, what does it end up being? So since it's symmetric, right? We want the point that has 30% up here. That's the 30th percentile. It's going to be this point.
Like 0.84. Wait. Wait. Can that be right?
So with symmetry, right? If we want 30% here and 20% here, well, so there's 30% is what we want, but up to the middle is 20%. I mean, it's up to 50%, right? So there's a 20% left over here. Right? And by symmetry, right, if this is 0.525 and this is negative 0.525 as the z value. So to get the 30th percentile, our weight is going to be our average, what's our standard deviation times Z. So it's 7.5, 1.2 is the standard deviation. And then it's negative because it's below the midpoint. And that ends up being 6.87. So the key to getting the percentiles below, right, is there's a symmetry, it's 50% to halfway. If you're not all the way up to halfway, 30th percentile, that means there's 20% to get up to here. This area is the same as that area, and we can look up the Z values are associated with that area, but it's a negative of that. So a few steps just to kind of see the logic of using the curves, the symmetry, the areas and the tails versus that, right? So a little practice, doing a couple of problems, and seeing how it goes if it works out. Let's do one more. We'll do one more example and get this up. All right, so let's imagine you have a stock, right, and the stock is trending up. You buy some. What is it, the chances of certain gains? One more numerical example. Let's say there's some stock, right? And you buy it at $100 a share. And let's say that this thing is trending up about 25 cents per day. So it's gradually climbing. People pushing the price up, they're buying it, willing to buy it higher because they think it's moving. But the standard deviation is $1 each day. So there's a lot of variability each day that's adding onto the variability. So this variability goes up and down each day, the next day it goes up and down and settles someplace. Right? And so one way of writing this type of model is that the price at day, let's say t for time, let's say the price at time t is $100 initially plus 0.5 and the average value times the number of days, plus an error, kind of some random variation. It won't exactly go up a quarter, it'll have some variability about there. And this amount of error really is the error, the variability that happens on day 1, plus the variability on day 2, plus the variability on day 3, plus the variability that happens on the last, right? So there's some randomness that is building up over time, right? Projecting into the future, there's kind of this upward trend, but there's this kind of increasing spread variability of the uncertainty about where this thing's going to be down, right? So you buy it. We could ask, what's the probability that the value of the stock is up at one day, at day 1? And let's say also that the prices are normally distributed. That's your assessment of the chances of it going up or down around that, the variability. It's kind of well described by a normal distribution. Right? The trend, the mean's going up, but there's this variability about it. What's the chance the stock is up after one day? At one day, what's the average? Well, under this description, if it's trending up by just 25 cents per day, then we're using as an average $100.25. A little increase, right, on average. After one day, if the variability, the standard deviation, it's only one of these kind of incremental errors in there. Just the standard deviation of 1 day, kind of how things normally vary for that stock. So the variance is 1. So the standard deviation is 1. So this would be our mu, this would be our sigma. What's the chance that it's up after 1 day? So the price at day 1, what's the chance that it's bigger than 100, right, that it's going up? So to answer this, we got a z-score, right? Let's change it back to standard normal with these mean and variances. So we're gonna subtract this, and so that's the chance that a standard normal is greater than, well, it's just 25 cents over that, so negative 0.25. So what is that chance according to this table? You need to look up the z-value. The standard normal is negative 0.25. Yes?
0.5927.
5927. So I'm going to put 0.5 first. We know it's bigger than 1/2 because the 0.25 is below the 0 point, so it's more than half the curve. And you looked up,
Yeah, I misread. It's 87, not
oh,
27.
if you look up 0.25, yep, that is 0.0987. 0987. So 0.5987. So about 60% chance you're up. Right? The thing's trending up. If there is no trend and it's completely flat, the chance that it would be above its mean is 50%. So because of that slight up, you get a slight chance up. If you draw a picture, right, here of that, say the standard normal, so here's 0, and we wanted the chance that it's greater than 0.25. This is kind of not really scaled very well, but can't. So we really want the chance that it's above this. But if we look up 0.25 on the chart, the chance we're in a sliver like this is 0.0987. So that sliver is the same as this sliver over here, plus we want everything that's above. Right, so about that. What happens after 4 days? What's the chance that this stock is positive after 4 days? But 4 days, what's the average? Start out at 100, and it goes up 25 cents per day, and we're at 4 days. The value of this thing would be $101 on average after about 4 days. And the error, that variability, by adding those things together, right? If these are independent things, if these are independent, and independent randomness. Independent randomness with mean 0 and a variance. Then the variance is add. So the variance becomes 4 after 4 days, 5 after 5 days, and so on. It's a very simple model with the errors. Variance is added. But we need the standard deviation, right? So the square root of that is 2. So now what's the chance that this stock at day 4 is gained? Yes.
I don't understand why it's a variance of 4. Because at the beginning we said the standard deviation is $1 a day. So how does that standard deviation of $1 a day become a variance?
So if a standard deviation of 1, the square of that is the variance of 1 as well. So and the variances of independent variables, when you add them together, end up added together.
Yeah, but like if if we had standard deviations to begin with, wouldn't we just add them together and not take the square root because we're adding standard deviations?
Well, so the way it works, so if you had B1 plus B2, these things are independent. Right, the relationship that works for sums of random variables. The variance of the sum of these things ends up being the variance of these. The variances end up being the thing that adds together. I guess we'll see more of that when we do kind of the multivariate linear combination thing. But so the first one is 1, and then the second one is 1. It goes up to 2. Right? So maybe we haven't really proved that or covered that as much. But if you add independent variables together, their variances end up adding rather than their standard deviation. So if you add up the variances, you can convert it back to the standard deviation we need for the normal by taking the square root. So, sorry if I haven't gone into that enough to explain it. But anyway, in this problem, I'm trying to create a situation now where the average has gone up by $1, but the standard deviation's also gone up as well. Right, so in this case, to calculate this probability, we want to z-score it. Sorry, it was 100. What's the chance that it's up? Is the chance that it's over 100. Right. So same idea. So we would take 100 minus 101 and divide by this new standard deviation. And it's the probability that a standard normal is greater than now negative 0.5. We're 1/2. Right? So we'll have our chances got up. So we had negative, we want to be negative 25 cents, or negative 0.25 here. Okay. Now in the second, 4 days later, with the same progression, we're negative down here at negative 5, right? So we actually have more area. Oh, next page. And so what's that chance? What are we gonna, is the value gonna be? What's the chance that a standard normal is greater than this negative 0.5?
0.5 plus 0.1915.
Above halfway, so of course below halfway, we add everything in there, and that sliver, right, 0.1915, right, 0.6915. And so it's going up, and as days progress, if you follow the same model, it becomes almost certain that eventually it'll be positive. Right. If you do a different question, though, what's the chance that it's at day 1, what's the probability that the stock is down 5%? The probability that the first one is less than, being down 5%. When it started at 95, when it started at 100 would be less than 95%. It's almost, if you work this out, so use a mean, it's $100.25, and a standard deviation is just 1. This one ends up being just about 0. There's almost no chance that it's down that far, because it's just not that much variability. Yeah.
Is that saying that it's down by 5% or more because it's in
Yes.
equal? Okay.
Yeah. It'd be 5% or more. Down 5% or more. Yeah. Right. So for these continuous ones, we're almost always going to calculate. We're not going to calculate at an exact point, because the actual chance that it's at one exact value is basically 0. There's an infinitesimal area under a point. You might calculate in an interval, say between 95 and 96, or 94.5 to 95.5 to capture that interval of one unit there, but it'll be an interval. In this case, a difference of a quarter, or sorry, 95 is about 5 units, but a standard deviation of 1, it just can't go that far. there's almost no probability out past 3d4. It's just so infinitesimal. If you repeat this though, say what's, at day 4, what's the chance that it's down, 5%? At day 4, the chance that it's less than 95%. If the mean, now the mean has gone up, the mean is higher, but the standard deviation is 2, and the square root of 4. It turns out that there is some chance that you would actually be down more. And that probability is down 5%. Is about point. It's still quite small. It's very small, but there's a little bit more probability that after time, because of that big variability, that you could actually end up trending down and be less. But anyway, so you can do all sorts of different calculations with these. Yes.
If we were given a standard deviation other than 1 to begin with, so
Yeah.
like if we were given that it's the standard deviation is $2 a day, would we have to square that standard deviation, add it together for the number of days, and then square root it again?
Yeah, right.
Okay.
So you would add up the variances, and we'll go through more when we do kind of linear combinations of variables to reinforcement. That would be exactly it. You take the standard deviation, square them, add them up, and then take the square root to get back to the other part. All right, so that's kind of some of these applications. Right? We're going to look at a couple other things with the normal. Right? One is we're going to look at its moment generating function. So I would say that this first part is more applied that we've done, right? Looking at calculations. Now we want to look at a little bit of the kind of theory and things that are going on with this. Right? So for a standard normal, what is its moment generating function? So it's expectation of e to the t. I'm calling the variable z, so I'll put a z in there. So just like, right, it has the same basic definition, right? We have to take the values, e to the t, z, times the density, and integrate that over the entire space. And the density for a standard normal was 1 over square root of 2 pi, e to the negative, right, z squared over 2 dz. Combine those terms there in the exponent, negative infinity to infinity, 1 over 2 pi square root, and then there's e to the negative. We're going to put 1/2 here. So this is e squared minus, always easy for me to write, e squared minus, and then we would have a 2tz up here. Yes.
Is that 2 pi? Or
Yes, it's the square root of 2 pi in here. So one thing we can do with that up there, so in the exponent, there's negative 1/2. Now z squared minus 2tz, right? To simplify that, one thing we can do is complete the square. Right? There's a z squared and there's a z here. But if we had something appropriate in there, it would be a square and you could factor it. So the thing that would be missing from making a square, right, is a t squared. And if a t squared were in there, right, that's z minus t squared. If we add the t squared in here, we have to make an adjustment, right, to make it all balance so that it's equal. And because of the -2, right, we have a negative 1/2 t squared, so we have to add on the outside, right, plus 1/2 t squared. And then that thing, like, we realize that we completed the square, z minus t quantity squared plus 1/2 t squared. We write that thing in the exponent, up inside the integral. We're going to have negative to infinity, 1 over the square root of 2 pi. There's an e to the negative 1/2 z minus t squared. And there's an e to the t squared over 2 dt. dz, right, for the normal. And I'll try not to switch between script z's and little z's too much. But for that integral, the e to the t squared is not changing, right? There's no z in this part, right? And it's multiplying that, so that part can come out of the integral. Right? T is just, you can think about it just being a number or a placeholder for a number, but it's not z. So it's not the thing that's changing in the integral. So I can pull out 1 over 2 pi square root e to the negative 1/2 z minus t squared dz. Right? Now that, right, this function in here, that thing, right, that looks like a normal density. Right? That's the general form of one of our normal densities. Right? This looks like a normal density with a mean of t and a variance or standard deviation of 1. And normal densities integrate to 1. So that goes away. And our momentary function is e to the t squared over 2. And this was so that the momentary function for a normal 0, 1 random variable. So that's the momentary function. The normal, the standard one, mean 0, variance 1, is not all that neat, right? Even though it's useful in terms of its means and variance and things like that, right? What did we do when we created do percentiles? Right, we did x equals mu plus sigma times z. So if z is normal 0, 1, the moment generating function of z was e to the t squared over 2. We just saw what's the moment generating function of x when we transform it. Before we do that, right, are there any questions on this completing the square? Probability things with normals, completing the square is, gets done a lot. Right? Things that are these quadratic forms in statistics, probability, applied math, often completing the square is a useful thing to do because then you get to write it as a simpler form and has a little extra leftover term. But anyway, that is how it goes. And recognizing this as a particular normal, in the general case, you subtract the mean up there, and you divide by the standard deviation, so the sigma doesn't show up there, but the t there is in the place that you'd have the mu, the mean, in the general formula. So it's a density. So this is the expectation of e to the t x. And if we put in e to the t, the equation there, mu plus sigma times z, those things are actually equivalent. And if you multiply these things out, e to the t mu plus t sigma times z, those things, I guess you can do one more step. E to the t mu times e to the t sigma z. And in terms of this expectation, right, The expectation's an integral. It's an integral with respect to the random variable, with respect to z in this case. That t and mu don't involve z. They're not random things in terms of the random variable. So in terms of expectation, those things come out. And we're left with the expectation of e to the t sigma times. Well, e to the t times z, right, was the moment generating function. And so here's a little thing here, t times sigma. So like we did a problem with the exponentials where we had e to the 3t and had a 3 plugged in there. Well, so this is the moment generating function of a standard normal evaluated at t times sigma. Because if it was just e times tz, it would just be the moment generating function. But we have t times z in the scale version. So we plug that in, tu, and then this one is a t squared sigma squared now over 2. The basic function is t squared. If we're putting t sigma in there, you get that in there. So this one ends up being t times mu plus t squared sigma squared over 2. So that's the moment generating function for a general normal. Moment generating function for normal, mean mu, and variance sigma, or standard deviation sigma, sorry. Variance sigma squared. So based on this, we should be able to get the moments, right? If we differentiate and set it equal to 0, right, we should get figure out the moments for that. But any questions on why this works? And I'm going through a series of steps. Let's find the moments. So x is normal, which means, well, that's what we're going to do. Sigma. We have a moment generating function. That's e to the t mu plus t squared sigma squared over 2. If we differentiate that with respect to t, we get that function back. So I'm just going to write that u of x of t again. And then we differentiate what's in the numerator up there with respect to t, right? So we just get a mu plus that exponent goes down to 2t, and so then it's sigma squared is there. This thing evaluated at 0, just the moment generating function evaluated at 0, is just 1. It's not of particular interest to us, per se. But if you put 0 in there, you just get 1. If you put 0 into this one, right, then that's going to be 1. Well, we can just kind of figure this out. Right? And then there's a 0 here, and all that's left is mu. You put 0 in there. And that's the expected value. Right? So for a normal, centered at mu, right, that mu has the meaning of the average. Take a second derivative. Well, second derivative, looking at this one, we're going to have a chain rule. We're going to have mxt times the derivative of this term over here, right? So there's a sigma squared that results. And then we're going to take the derivative of the first one times that, u plus t sigma squared. And if we set t equal to 0, we're going to get 1, and then sigma squared. The m prime of t at 0 was our mean, so that's mu. And when 0 is here, the sigma goes away, and we just get a mu squared. So that is the expectation of x squared. What's the variance? The variance of x, expectation of x squared minus the expectation of x quantity squared. So sigma squared, mu squared minus the mean squared, which is mu squared, or sigma squared. And so sigma squared, in fact, is our variance. It's a symbol in the density, but it turns out to be exactly the variance. You could have defined, set up the normal with the mean, mu, and sigma. You could have done 1 over sigma as the parameter. You could have done mu over sigma as a parameter. You could have done a lot of things to make those symbols be different and still get the same density function, the same bell-shaped curve. But the way that we have it set up, it's the mean and variance. So it has that nice interpretation. What's the third derivative? Keep going, right? So it'll be the first derivative of this term, with the sigma squared multiplied onto it. And then this one gets the chain rule applied to it. So if we take the first term and the derivative of the second one, right, there's the sigma squared again, plus the derivative of the first term times the mu plus t sigma squared. So if you put in t equals 0, the first derivative was mu, and then there's a sigma squared. But there's 2 of those, so there's 2 in there. And the second one, right, was sigma squared plus mu squared. And then there's a mu, right, because the t equals 0 there. So this third one ends up being 3 mu sigma squared plus mu to the third. Right? That's the third moment. So that's the third regular moment. We're going to use these to figure out what's the third centralized moment, right? What's x minus mu cubed? X minus mu cubed. Any guesses of what it would be? What we're going to do is look at x minus mu quantity cubed. Remember, our density looks like this, centered around mu. So if you take the x cubed minus 3x squared times mu plus 3x mu squared minus mu cubed, and I take the expectation of these separate pieces, this one was the 2, well, that's the third moment. So it was 2 by this one, 3 mu sigma squared. Is 3 mu sigma squared. Double check mine. Plus a mu cubed. 3 mu sigma squared plus mu cubed. That's that first term. Minus 3. This one was sigma squared plus mu squared times mu. This one, expectation of x is just mu, so it's 3 mu squared mu cubed. And then this one's just a constant. So what does this thing end up being? There's a 3 mu sigma squared and a 3 mu sigma squared there, so those are gone. There's a mu cubed, minus 3 mu cubed, and then 3 mu cubed and a minus mu cubed. So this one and that one, that one and that one. So it's just the, yes?
Why did we do that?
So why do we do this? We're kind of, so there's this is the third central moment. Right?
So that's skew.
Why, this is related to skewness, right? What's the, x minus mu on this side is positive, right? X minus mu on this side is negative. And it's symmetric, so these things exactly balance out. And so you would kind of expect this, thinking about symmetry and that this x minus mu cubed is related to that, is it being 0. And so if we push this work with the moment generating function and actually find out what this is, yeah, it shows that it's 0. If we did it with other distributions, they wouldn't be. What any of these gammas or certain betas, or exponentials. The skewness is not going to be 0. It's going to be positive or negative. And so looking at some data and variables, in addition to computing means and standard deviations, you have, say, 100 variables you're looking at, you might very well compute skewness as a measure to identify quickly ones that are possibly more extreme and harder to deal with in terms of modeling, in terms of prediction, because of its lack of symmetry. But it's one use of the moment generating function and pushing that use a little bit more. But any other? So one other use we had of moment generating function is if you have two random variables and you add them together, and x1 and x2 are independent, then the moment generating function of the sum is the product of the moment generating functions. And so if x1 is normal with some mean and some standard deviation, and x2 is another sample from a normal, and then we take the sum, what's the probability distribution associated with the sum? If these are two stocks, you have two stocks, two investments, and add them together, what's the total? What's the distribution governing that? What are your chances related to that? Or if these are two test scores, two grade components added together, and one is normal with a mean and standard deviation, and another is normal with a mean and possibly different standard deviation. You add them together, what's the distribution? Is it still normal, or does it turn out to be something other than that? Can we say anything? Well, moment generating functions can help us in this case. Assume these things are independent. So the moment generating function of the sum, and the moment generating function of the first one, and the moment generating function of the second. I wrote that. And if they're normal, right, then there's an e to the t mu1 plus a t squared, sigma squared 1 over 2. And the second one is e to the t mu2 plus a t squared, sigma 2 squared over 2. Right. And if you combine these things, right, what's it going to look like? Right. Combine those terms, and you can combine these terms. So what? Do we recognize that moment generating function as anyone we're dealing with? We recognize that kind of as the form of the normal, right? There's a t squared up there, right? With a multiplier on each of those. The 2 is there, right? So it turns out that the sum is again a normal random variable. And the mean is mu1 plus mu2. And the standard deviation that you'd want to use for this one, well, the variance is sigma 1 plus add the variance, and so the standard deviation is the square root of the thing. So it's another normal. So if you have these two very different measurements and you're adding them together, it's still, and they're both individually normal and they're independent, they both end up being, the sum ends up being normal. So you can calculate the probabilities over, that the sum is over value, that the sum is in some range or anything like that. What happens if we take the difference? So we're going to get x1 minus x2. And again, x1, x2 independent with the normal distributions that we had before. Well, this is like the moment generating function of x1 minus x2. This is like x1 plus the negative 1 times x2. So this should be, if we think about this as a moment generation of, negative 1 times x2, the thing we did with the moment generating functions and scaling it, this would be the moment generation of the first one, and then the moment generating of the second one evaluated at negative 1 times t. Before we had a scalar, like multiplied by sigma, we got sigma times t, and now we have like a negative 1 times t. So this one will be e to the u1t plus t squared sigma squared 1 over 2. And this one, well, if t is negative here, right, it's a negative mu 2t plus, but what happens to the negative 1 when we square it? Right? Square it, get rid of that. So there's a t squared sigma 2 squared over 2. And to combine those things, e to the mu1 minus mu2 times t plus so t squared. And again, the variance is add. Even though we're taking the difference, the variability of this, the difference is the sum of the variabilities. That squaring in the variances get rid of the negative effect. It's not like they cancel out or any other. So all that says that x1 minus x2, this difference should then still be distributed as a normal distribution because this matches the normal term with a t and a t squared in there. The average is the difference. And the variability of the difference is the sum of the variances. So even though we're taking the difference, we don't subtract the variances or anything like that, but the variances add just as before when they're independent. So based on the moment generating allow us to do things like that. But any questions about? Yeah.
So how come that's the variance, but the one before is the standard deviation?
Well, you could say, converting it between the two, then the standard deviation is going to be sigma 1 squared plus sigma 2 squared. So you can take the square root of that and call it the standard deviation. Different books really do different things. Whatever you're going to do, you're going to have your variable, generically calling it x, minus the mean divided by the standard deviation, which is z-score, the probabilities there. So always just keep track of whether it's a mean or standard deviation. But variance is add rather than standard deviations. That's the way that it works out. But any questions about normals? So I think that's probably enough for today. We'll come back on Tuesday. We'll start looking at things in chapter 6, which are multiple variables together, a little more elaboration on these joint distributions and things. There's a homework due, so have that homework. I'll pick that up before we go.
Yeah.
appreciate your coordination of your plan with your.
I'm sure.
I'm sure, like, except for
Well, sure, please.
Well, yeah, but well, even that, like, I guess the bank.
You're adding
Yeah.
two words together?
Yep.
T squared over two. So why is it still over two? Wouldn't it be T squared, so it must. Oh, because it's the different.
Well, so yes, look, we have t squared sigma 1 plus they both have their one half in there. Sorry.
I'm good on
Thank you. Thank you.
hash function, yeah, so.
Thank you.
That was the first question. Was, you know, confidence in good